In this session, I'm going to look at some of the common probability distributions. The reason why I need to look at this particular topic, just to understand, most of the times the investment decisions, or for that matter, any decisions that we are making, they are based on random variables. We are not sure on the outcome of the event, right? If I want to purchase a particular stock, I'm not sure whether the price of the stock will go up in future or go down. Means there is a lot of involvement of probability in our investment decisions. So majority of the variables that we are looking at in our day-to-day life, they are all random variables. So once they are random variables, all I can make is only probabilistic statements about those random variables. I can only make statements subject to different probabilities because there is an uncertainty. So that is where, if I understand the pattern of the probabilities, and that patterns are what are getting converted into different kinds of distributions based on probability. So once I understand the different kinds of distributions, I can try to map the behavior of my random variable with that appropriate distribution. So we'll talk about a few commonly used distributions in finance. Probably I can look at something like uniform distribution. We'll talk about something called binomial. We'll talk about normal distribution, a few of them which have a decent number of applications in the world of finance. We also look at the log normal distribution. These distributions, the understanding of them, they have lots and lots of applications in finance. The option pricing, the derivatives pricing models, they use a good, they make a good usage of these probability distributions. And even if I want to understand the statistical inference making, which is a part of inferential statistics to make conclusions based on the data, even there the understanding of the distribution become more and more useful. So that is where we should start understanding the concept of probability distribution, so that we can map them towards the decision making process, right? So as a part of that, I think that we should look at the concepts which I am covering here. I would be covering a few discrete random variables, in fact talking about a couple of important discrete probability distributions. Then I'll spend some time in terms of understanding the continuous random variables and continuous probability distributions. A few of them are called as continuous probability distributions, a few of them are discrete. And towards the end, I would just focus on how we can generate these kind of distributions, right? How we can generate the data in case I don't have the data. How can I generate the data which is following a particular distribution? How can I generate the data which is following, let's say, binomial distribution? How can I generate a data which is following a normal distribution using a mechanism called Monte Carlo simulation? So these are the different topics that we will cover as a part of this particular session. So initially, let me get started off with the discrete random variables or discrete probability distributions. So once I know that a random variable is nothing but the outcome is uncertain for it. Whenever I talk about a random variable, if I look at it in simplicity, any variable whose outcome is uncertain based on some kind of probability, we are associating it to a random variable. Now this particular random variable, if it takes countable number of possibilities, countable number, again, it could be limited like a roll of a dice. The possibilities are only 6, 1, 2, 3, 4, 5, 6, or it could be even unlimited but still countable. It could be some hundreds, thousands, but okay, only numbers, only integers, they are still countable. So all those things, even if it is very few in number, a very small finite set, or even if it is infinite kind of a set, but as long as it is countable, we call that particular random variable as a discrete random variable. But on the other side, if the possibilities are completely uncountable, if the different outcomes are completely uncountable, probably if I look at the heights of the person, depending on the precision of measurement that I am using, any decimal value can come out. Probably if I am looking at it in centimeters, I could have 151, 152, or probably I can even go to 151.11, 151.12, or probably I can go even into a millimeters or micrometers and probably talk about a few more decimal points. Similarly, when I look at the rates of return, almost any number of values after the decimal point are possible. So what are the possibilities? I cannot literally count. Whereas if I am saying age in integers, it is still a discrete. Probably it can go right from 1 to 100 or 1 to 150 or whatever it is, depending on the minimum age to the maximum age. So it might be infinite, but it is still countable. So whichever the variables are more and more countable in nature, I call them as discrete. Whichever are uncountable, they are continuous. But sometimes in real world, what happens is, if the numbers are too large, we approximate it to a continuous. Numbers being too large, so which means in reality, probably creating a situation of continuous, creating a situation of discrete, there is a very thin line. Probably if I am talking about the stock prices, though almost any price is possible, probably the stock prices will increase in the rates of, let's say, 5 paisa. So though there are unlimited possibilities, but I can't get 151.08. So which means it's still a countable but a discrete set. But because so many values are possible, I may try to approximate it to a continuous. So that is the kind of a choice the user is having, whether he wants to use that particular variable as a continuous or a discrete. Because as the number of values increase, the discrete can be approximated to a continuous and vice versa. Probably a continuous can be taken in the form of a discrete, or a discrete can be taken in the form of a continuous, because at the end, for me, any distribution is nothing but it's a kind of a visualization of the possible frequency distributions. So generally, visualization of the possible frequency distributions of the future is what is coming out as a part of my understanding of a distribution. So it's a kind of a mathematical or modeling of the possible random possible outcomes that are going to come up in future, along with their associated probabilities. So that is what is typically coming out as a definition of a probability distribution. Now, when I look at a probability distribution, we talk about, whenever I talk about a probability distribution, especially discrete or even continuous, whenever I use the word probability distribution, we actually define two important words here. One we call as probability function. The other we call as cumulative distribution function. Whether it is continuous or discrete, we have two different definitions or two different dimensions of any probability distribution. First, I look at a probability function, wherein I talk about what is the probability that any random value will take a value equal to x. So which means when I throw a dice, what is the probability that the random variable x, which is the value that comes up on the dice, is equal to 1? Or what is the probability that the random variable takes an even number? So this is what I'm calling as a probability function, where we are talking about the probability that the random variable takes a specific value. So this is generally represented by a simple small p of x. P of x is what we represent as probability that x equal to x. So this is called p of 1, probability that x equal to 1. But the same thing, when I take it in a continuous case, we don't use the word probability function, we use the word as probability density function. That's the only difference. The naming is different when I use continuous, but when I'm using discrete, I'm calling it as a probability function. And instead of p of x for a probability density function, we call it as f of x. And a few important things relating to this p of x, especially the discrete case. What I see is this p of x, just because it's a probability, it will lie between 0 and 1 inclusive. It cannot be less than 0, it cannot be greater than 1. So for any particular probability, the value of p of x, the probability function's value at any particular point, will lie only between 0 and 1. And if it is if it has to be a probability function, when I am summing up the values of all probabilities, sum of all probabilities for different occurrences of the random variable, different occurrences or different outcomes of the random variable, that summation should become 1. So these are the two important things that needs to be met for this particular, for any particular function to be called as the probability function. Any function is called as a probability function if the individual probabilities all are lying between 0 and 1, and the sum of the total probabilities for the various outcomes that are coming for the random variable, that is going to be 1. Now, moving on to the other side. See, in most of the cases, I may not be interested in finding the probability of one single value. I may be interested in a range of values. Probably it's like, what is the probability that x takes a value less than or equal to x? When I throw a dice, what is the probability that I get a value less than or equal to 4? So this kind of a representation where I talk about less than or equal to kind of a case, we call that as the cumulative distribution function, CDF. which is generally represented with capital F of x both for, so in this case I call as f of 4, which says probability that x is less than or equal to 4. If I say f of x, the probability that x is less than or equal to x. This is the same that applies both to discrete as well as the continuous distribution. So all it says is the probability that a random variable x takes a value less than or equal to the small x, which is 4. So this is like all we do is we find out probability of x equal to 1 plus probability of x equal to 2 plus probability of x equal to 3 plus probability of x equal to 4. So we are accumulating it, we are summing the different probability functions, we are summing the values of the probability function for all the different outcomes less than or equal to 4. So that's how we are building a cumulative distribution function. So this is a general characteristic of any probability distribution and probability distribution functions. Now we can get into the understanding of specific probability distributions. The initial probability distribution in the discrete space, I would like to look at the uniform distribution. The discrete uniform distribution, which has lots of applications. One major application is this is a base for generation of random numbers, which has applications in Monte Carlo simulation, which I am going to deal with sometime towards the end. Now let's take the example of a throw of a dice. So the random variable x can take any value 1, 2, 3, 4, 5, 6. Now because it is taking a limited set of values, 2 countable number of observations, so I say that this is x is a discrete random variable. Now I want what is the probability of x. What is the probability that x equal to 1? 1 by 6. What is the probability that I get 2 on the dice? 1 by 6. What is the probability that I get 5 on the dice? 1 by 6. So the probabilities that I am getting x equal to 1, 2, 3, 4, 5, 6. So these are the numbers. Now which means here, is it first of all a probability function? If it has to be a probability function, yes, all individual probabilities should be greater than or equal to 0, which it is. The sum of the individual probabilities for all the possible outcomes is equal to 1. Even that is getting met. So that's the reason I call this first of all as a probability function. This qualifies as a probability function. And whenever I have all probabilities being equal, means the different outcomes and all of them have equal chance of occurring, that is what I call as the discrete uniform distribution. Uniform, the probabilities are uniform across. So that's the reason we call it as a discrete uniform distribution. So let's try to understand a few things regarding this discrete uniform distribution. Let me try to take it into a spreadsheet. So I'll take the example of a throw of a dice, x, and I am also taking the probability of x. So x can take any of the values 1, 2, 3, 4, 5, 6. And we have seen that the probability of occurrence of each of them is 1 by 6. So all of them have 0.166 kind of a chance of occurring. Now cumulative, if I want to take capital F of x, which is the cumulative probability of x less than or equal to x. So for the first one I'll take it as it is, and from second one onwards I'll to the previous cumulative I'll add the probability of the current, so which becomes f of x at any stage. So this is how the f of x is changing. So if at all I want probability of x less than or equal to 4, then I can directly look at the cumulative distribution here saying 0.667, and that is what I say, that the probability of x less than or equal to 4, which is nothing but probability of x equal to 1, x equal to 2, x equal to 3 and x equal to 4. Or even sometimes if I want to find out what is the probability that x lies between 2 and 4 non-inclusive. It's lying between 2 and 4 not inclusive. Only x equal to 3 is what I am interested. So I'll say that it is still 1 by 6. So what could very well happen is, once I have a probability function in place, once we have a probability function in place, we can very well find out the probabilities of any kind of combinations. We can find the probability of one single value, or probability that a random variable takes a value in a particular range, or probably a probability that the random variable's value will be less than or equal to something, right? And here let's try to look at the graph. Let's try to plot both the p of x as well as f of x. Right, let me try to plot the graph both for p of x as well as f of x. And what we are seeing is p of x is completely flat. Right, I'll take the axis labels. So what we are seeing is p of x is completely flat, but f of x is more looking like a continuously increasing kind of a function, right? F of x is continuously increasing. F of 1 is this much, f of 2 is this much. So less than or equal to 2 here, probably a little bit of more fine tuning is required. But what we are seeing is f of from, let's say, from 7 onwards, there is no probability of occurrence, which means after that it is going to be flat out itself. So the cumulative distribution function always lies between 0 and 1, and as x is increasing, the cumulative distribution is either increasing or staying flat. All right, now just to understand, let's say I want to find out the expected value of x here. So expected value of x, probably I'll get it as the x times the p of x. So this multiplied by this, and probably here first let me compute x times p of x, and after I add up all those, that is what I get as the expected value of x. So I sum up all these, the expected value of this particular random variable is 3.5. Similarly, if I want to go ahead with the computation of the variance, I can take it as x minus expected value of x whole squared multiplied by the probability of x. That is what we generally do. So here also I am doing x minus expected value of x whole squared multiplied by the probability of x. So all put together. So here I can find out the variance of x, which comes out as a summation of these specific values, and based on that I can find out the standard deviation of x, which actually works out as the square root of the variance. So probably this I can call it as the discrete uniform distribution. So this is the expected value, this is the variance, this is the standard deviation. Now in general also, without doing all this, if at all I am talking about a uniform distribution, taking the values between A and B, which are equally spaced, and all of them having an equal probability of occurrence. So if there are n specific values, so in this case 6, so the expected value simply is A plus B by 2, the minimum plus maximum by 2, 1 plus 6 by 2, which gives me 3.5. Even here we have got the value 3.5. Similarly, I can find out the variance of x using n squared minus 1 by 12. So n is the number of possibilities, where each possibility will have a probability of occurrence of 1 by n. So in our case it becomes 6 squared minus 1 by 12, 35 by 12, which works out actually to this 2.91. So if at all I know that the distribution is a uniform discrete distribution, I don't need to really compute the expected value by doing each observation with the corresponding probabilities and then trying to add up. I don't need to do all that, because this is directly coming out with A plus B by 2. Similarly with the variance, and once I know the variance, I can very well go ahead with the standard deviation. So these are some of the important things that are associated with the discrete uniform distribution. Now the next important distribution which I am going to look at, again in the discrete category itself, is a binomial distribution. Generally, whenever I am looking at my result, the future, when I am trying to predict the future in the form of only two possibilities, success or failure. Whenever I am planning to look at my result in the form of success or failure, only two possibilities, that is where we are talking about binary. My result is taken in the form of success or failure, and if I really want to assess out of n times I have done something, what is the probability that I have got x successes? So I am planning to actually do a record of the number of successes or failures if I am doing some experiment so many times. That is where we take the help of binomial distribution. So binomial distribution helps us in analyzing the pattern of number of successes or failures in the performance of a similar experiment done many times. Similar trial performed many times. I want to observe the pattern of the number of successes or failures. This has so many applications in the financial space. There is again an option pricing model that is developed, which is purely on the concept of the binomial distribution, assuming that the stock price will either go up or go down. Some probability that it will go up, some other probability 1 minus p that it will go down, again over successive periods of time. So over if I say that the probability that it will go up in 1 month is p, it will go down in 1 month is 1 minus p. So probably if I am looking at within 2 months, within 3 months, so which is like a multi-period, and the chance that the probability is going to go up at the end of 2 years, 2 months or 3 months. So this is the kind of a concept which is again using only two possibilities. If it goes up, probably I can treat it as a success, goes down, I can treat it as a failure. So at the end, whenever I am looking at only two possibilities, success and failure, and I am trying to model the number of successes or failures when an experiment is performed some n number of times, That is what is can be the behavior of that kind of a random variable can be characterized using the binomial distribution. And the base for this binomial distribution is the Bernoulli trial. Whenever I say the Bernoulli trial, we are only talking about that experiment will produce only one of the two outcomes, success or failure. So when I do a trial, either it is a success or it is a failure. Probably it could be a success with a probability P, it could be a failure with a probability 1 minus P. Now binomial theorem, what it is, binomial distribution, what it is saying is, if the same experiment is repeated n times, if the same Bernoulli trial is repeated n times, I can have a 0 success or 1 success or up to n successes. Now, how many successes, the number of successes I have is a random variable here. So, I can have 0 success, 1 success, 2 successes. So, this is where I am trying to use the binomial distribution. If I know for one single trial, the probability of success is P, the probability of failure is 1 minus P. If the same trials are repeated n times, if I have to get x successes out of n, means n minus x could be failures. So what is the typical probability of getting exactly x successes? What is the probability of getting at least x successes? So whenever I am trying to model the probabilities associated with the number of successes, that is where we are referring to a binomial distribution. So here the binomial distribution gets characterized by two major parameters. One, in an independent trial, what is the probability of success of the particular event? Of a particular trial, what is the probability of success? So obviously once I know P, the other part 1 minus P is directly known, which is the probability of a failure. And the other important thing that I need to know in case of a binomial model is how many times the experiment is performed. Number of times the experiment is performed. So these two are the important parameters, but yes, a few important assumptions also that got made. The P, whatever I am talking of, which is the probability of success of one trial, I am assuming that the probability of success is constant for all trials. One important assumption. Probability of success is constant for all the trials, which means if I had 10 successes, probably it doesn't mean that the 11th one is having more chance of a success. Whatever is it for one event, it's constant across, and the events are completely independent. There is no interdependency. So wherever we are talking about interdependency between the event, I cannot use the binomial distribution model. All the trials need to be completely independent. If that's the case, I can look at the random variable x following a binomial distribution characterized by two parameters, the number of trials and the probability of success of the trial. And whenever we are talking about what is the probability of x successes, all we are saying is it goes with the formula NCX, probability of success to the power x, probability of failure to the power number of failures. X successes means n minus x failures. So because the trials are independent, the probability of a success is P. So I am talking of x successes, so it becomes P power x, and the failures are 1 minus P. Probability of failure is 1 minus P, and the number of failures are n minus x. But in each of them, so many combinations. So first one could be a success, second one could be a failure. So out of n, if I have to choose x elements which are going into success, I can choose them in NCX ways. We have discussed that in a combination. If at all I want to select x items out of n, I can do it in NCX ways. And we just to define, NCX is nothing but n factorial divided by n minus x factorial times x factorial. So the probability is coming out in this particular manner. So probably let's try to look at a small model that is associated with a binomial distribution. We'll create a small model associated with a binomial distribution. Let's say I'm doing an experiment 10 times. The probability of success of that particular experiment is 0.5. So obviously I know that the probability of failure will be 1 minus that, which is again 1 minus 0.5, still 0.5. Let's say I want to track the different successes. What is the probability that the number of successes, x I am treating as the number of successes, right? So it could be 0, it could be 1, and it could be anything up to 10. So here I want to find out what is the probability of success. I can very well find using that NCX kind of formula. So NCX, here I have a formula combination. So n is 10, x is 0. Out of 10, what is the probability of getting 0 successes? Multiplied by probability of success to the power number of successes, multiplied by probability of failure to the power number of failures. I'll take it as 10 minus the number of successes. So this is what is giving me that this is the probability of getting exactly 0 successes. Similarly, I can extend it to say that this is the probabilities of getting 1 success, 2 success, 3 success, and n number of successes. Now, first of all, is this a probability distribution or a probability function? All the probabilities are lying between 0 and 1. So it's a probability function. The sum of all the probabilities is coming out to 1. So even this is meeting the criteria for a probability function. Now I'll try to draw a small graph associated with this. If I am trying to draw a small graph associated with this, it is showing some kind of a symmetricity, right? Either I can plot a line chart. Let me not plot a line chart because it's showing continuous. I'll go with a simple column chart. Okay, here it is showing some kind of a symmetricity, right? Probably there is a gradual fall on both sides and some kind of a symmetric behavior is coming up in the graph. But just let me try a different thing. Instead of putting a probability of success to 0.5, let me put it as 0.1. If I am putting it as 0.1, all I am seeing is it's becoming a completely positively skewed kind of a data. So if the probability of success is less than 0.5, I see that it becomes a complete positively skewed kind of a distribution. And look at it the other way. If the probability of success is greater than 0.5, it gets completely as a negatively skewed kind of a distribution. And on the other side, if the probability of success is 0.5, I see more of a symmetric kind of a distribution. So probably this is one important characteristic that is associated with the binomial distribution, that in some cases it exhibits a symmetric behavior, whereas in some other cases it shows completely skewed kind of a behavior, right? So the more extreme the probability of success is from 0.1, I'm seeing a completely skewed kind of a behavior either towards the positive side or towards the negative side, right? So that's one more important point for us to understand as far as the binomial distribution is concerned. And just like a uniform distribution, here also I am interested in finding out the expected value as well as the variance. So even if I try to compute the expected value by doing all this, what gets simplified for us is at any point in time, the expected value of the binomial distributed random variable, just even that mechanism, if we are trying out, the expected value comes out very simple, n times p. So n times p is the expected value of this random variable. So the expected value comes out to be 5. I can do this exercise as well, but I am going to land up in just np, which is 5. And the same way, when I try to find the variance of this binomially distributed random variable, variance comes out as np times 1 minus p. So np, which is np times 1 minus p. So to a large extent, what we can very well observe is variance should be less than or equal to the expected value. The variance should be less than or equal to the expected value. Why? Because variance is actually coming out as expected value times 1 minus p. And 1 minus p will always lie between 0 and 1, because p always lies between 0 and 1. 1 minus p also lies between 0 and 1. So the max it can be equal to expected value if 1 minus p is 1, which means p is 0. The probability of occurrence of an event is 0. Then the variance is equal to the expected value. Otherwise, the variance will always be lesser than the expected value. And of course, the standard deviation I want to find out, which is nothing but the square root of the variance. So standard deviation is coming out with that particular mechanism. And in many of the cases, in a practical scenario, if I have to look at, probably it is applicable very heavily in modeling stock price tree. We could look at, if this is the stock price today, it can either go up with some probability or go down with some probability in the next 1 month. So if it goes up again from there to the next 1 month, again there could be a probability of p for the upward movement, 1 minus p for the downward movement. Or probably again, if it has gone down in the first, again there could be a probability of p for the up, 1 minus p for the down. So at the end, if I really want to find out what is the probability that at the end of 2 periods, what is the probability that it will reach this particular value? So which means the probability of 1 up and 1 down, or 1 down and 1 up. So what is the 1 down and 1 up, or 1 up and 1 down? So the probabilities are p times 1 minus p, 1 minus p times p. So overall it becomes 2p times 1 minus p. So we can very well try finding out what is the probability of a value either reaching a particular state or going above a particular state, going below a particular state, in case we are trying to model it as a binomial distribution, especially when we have a value taking on a random variable taking only 2 values, success or a failure, and I am trying to model the number of successes once a particular experiment is repeated n number of times. So that is what can be accomplished using the binomial distribution or a binomial random variable, right? So these are the two important discrete distributions that we need to be comfortable with. Now with that as a base, let's try to understand a few of the commonly used continuous distributions also, which can really help us in taking some kind of a decisions or conclusions in finance. All right. So as we have earlier talked of, whenever we say continuous random variables, the possible outcomes are uncountable, correct? And if at all I know that we have got a particular value for the height, probably 165 centimeters, I don't know what is the next highest value. It could be 165.01, it could be 165.001. So I don't know what is the next highest or next lowest. Means literally the possible values could be anything between minus infinity to plus infinity on a real world space, and a set of real numbers or some subset of them, but within each small interval there could be numerous possible values. And that's the reason for any continuous, we don't define the probability of a particular value, a random variable taking a particular value. Whenever I say the probability of random variable taking a particular value, we generally take it as 0, because there are numerous possibilities, and because of that a random variable taking a value exactly equivalent to this particular value is almost negligible, because there are infinite kind of possibilities. So the probability is just like 1 by infinite, which will be as good as 0. So generally in case of continuous, we talk about the probabilities only in a range, not per one single specific variable, right? So now with that as a base, let's start off with the understanding of three important distributions here. A continuous uniform distribution, which we have looked at even in discrete case. I am looking at it in a continuous case. I would also talk about the most commonly used distribution in many real world applications, including the financial applications, the normal distribution, and a slightly different version of the normal distribution, which also has a lot of applications from a finance perspective, the log normal distribution. So let's get started with the continuous uniform distribution. Just like a discrete, the continuous uniform distribution is having a kind of a uniform values across a particular interval. The probabilities are more or less uniform. So whenever we are defining the probability function for a continuous function, we said we will define a probability density function. Just like a probability function in case of discrete, here we talk about a probability density function. So for a uniform distribution, we talk about the probability density function as 1 by b minus a, as long as x is lying between a and b, and it is equal to 0 if x is less than a or x greater than b. So as long as x is in between a and b, the probability of occurrence of x is 1 by b minus a, which is uniform. So if I want to know the probability, the probabilities between 0 and 10, right? I want to find out I know that x lies between a equal to 0 and b equal to 10. Then The probabilities I can find out f of x is nothing but 1 by 10 as long as x is lying between a and b. So if at all I want to plot a graph, this is what is the graph that it looks like for a continuous. Almost all the values are uniform, so it's a straight line. And if at all I want to look at a cumulative distribution function, it's just like an addition. Because it is continuous, we actually don't do an addition, because it's as good as probably doing the additions across all the minute changes of intervals. So the same thing when it comes into finding the cumulative, or probably if I want to evaluate the probability of a less than or equal to x less than or equal to b, it's as good as saying you integrate. We perform the integration between a and b, the f of x dx. Whatever was the summation in a discrete form, here we call as integration in a continuous form. Right? So, probably here, if I want to find out the probability distribution of f of x, it means I'm trying to typically look at adding up the probability density function over the entire area of 0 to x, and that is what I am calling as f of x. So first what we do is we have taken, let's say, the PDF, probability density function. So if I am saying a is 1 and b is 10, a is 0, b is 10. So what we are simply saying is f of x is 1 by b minus a, 1 by 10. So my graph of f of x for x equal to 0, 1, 2, as long as x is between 0 to 10, the f of x is 1 by 10. Now if I want what is the probability that x is less than or equal to 3, that is what is the cumulative distribution function f of 3. So it's nothing but, once I have a density function like this, I take the area of this density function with respect to the x-axis. With respect to the x-axis. So this is nothing but, it's a rectangle. Now I am treating this rectangle and I am finding out the area of this rectangle. This side the length is 3 units, this side it is 0.1. So the area of this rectangle is 0.3. So we say f of 3, which is the cumulative distribution function, is equal to 0.3. And that is what we call as integration. Finding the area of the rectangle, or finding the area of the probability density function. Whatever the area I want to find, I'll integrate it. Probability of the area of the area of the probability density function within the limits over all minute possibilities of the changes in the value of x. So just like, instead of doing that, it's like, okay, you divide this x into so many small pieces. You divide this x into so many small pieces. Try finding out the individual areas. Add up all the areas. That is what we typically call as the integration over the range. We are saying integrate f of x over 0 to 3. And just to simplify, in case of a continuous uniform distribution, this f of x will come out as 0 if x is less than or equal to a. It gets evaluated as x minus a divided by b minus a, as long as x is lying between a and b, and again it will be 1 if x is greater than or equal to b. So if at all in this question, if I had to find f of 3, I could have taken it as 3 minus 0 by 10 minus 0, because x is, as long as x is lying between a and b, I can use this formula, so I can take it as 3 by 10 and 0.3. And that is what comes as a part of even this expression, the integration between 0 to 3, f of x for me is 1 by 10 dx. So the integration of 1 is x, and x I am substituting the limits 3 and 0, 1 by 10 times 3 minus 0, which comes out again as 0.3 only. So whenever I am using this kind of a notation, it means that I am trying to sum up for all small changes of x. I am trying to find out the area of f of x. I am trying to divide this x into very minute intervals, the interval of 0 to 3. I am trying to divide it into minute intervals and trying to find out the area of each of the interval, and I am trying to substitute, and I am trying to sum up all those kind of stuff. So that is what is the typical meaning, and majority of the times the integration either I perform manually if I know the integration values, and in majority of the cases integration is handled through numerical methods. Different kinds of integrations. There are so many numerical based mechanisms to handle the integration. There is a midpoint rule. There is a trapezoidal rule. There are different kinds of rules where I can convert the integration into a kind of a basic numerical calculation. There is a Simpson's rule. There are different such kind of rules that are there, which typically convert the integration into a numerical method, and typically it solves that particular integration value or the area of that particular probability function within a particular limit or within a particular interval. So, and another important point associated with the continuous distributions is all these are more or less the same. Probability of A less than or equal to X less than or equal to B. Probability of A less than or equal to X less than B. Probability of A less than X less than or equal to B. Probability of A less than X less than B. In a continuous case, all these four are equal. The reason being, the probability of X equal to A, one single point, is always 0. The probability of X equal to B, one single point, is always 0. So because of that reason, the boundaries do not create any kind of impact. So any of these four, whether I represent whether I want to look at any of these four, all of them will look out to the same mechanism of integration between A to B, f of x dx. This is one important thing, because in case of discrete, it matters very heavily whether this particular value needs to be included or excluded, because that the border value is what that carries a lot of that could carry a huge probability. That point itself could accumulate a good amount of probability, whereas in case of continuous, that cannot happen. For a particular point, the probability is always 0 in case of continuous. And just as a quick workout with respect to continuous uniform distribution, if I want the mean of it, it is nothing but a plus b by 2, just like your discrete case. But if I am looking at the variance in case of a continuous uniform distribution, I look at it as b minus a whole squared by 12. In case of continuous uniform distribution, the variance comes out as b minus a whole squared by 12. Whereas in case of discrete uniform, the variance comes out as n squared minus 1 by 12. So that's a few important things that we need to have a comfort on as far as the discussion relating to the continuous uniform distribution is concerned. All right. Now, the next thing that we are going to look up is one of the most useful distribution as far as the applications of finance are concerned, the normal distribution. Very heavily used. Probably a theory called modern portfolio theory, or probably a majority of the risk management world, determination of value at risk, which is one of the key revolutions in the risk management space. All of them use the concept of normally distributed data in some form or the other. And even in non-financial applications also, wherever I want to use the statistical inference, right, wherever I am using the statistical inference, or probably wherever I am using the concepts of regression, which is a statistical technique, all these, they are typically used almost in every field. And what we see is these are all enhanced by using normal distribution, because they all get guided by a theory called central limit theorem, which I'll discuss probably in the next session. But they are guided by a theorem called central limit theorem, which extensively uses the concept of normal distribution. Because all the central limit theorem, on a very broader note, what it says is, if the variables are large in number, if the number of values are large, number of variables are large in number, the mean of those variables is going to follow a normal distribution. The means of the values of large samples is going to follow a normal distribution itself. That's a kind of a revolution which enhances the world of statistical inference and regression mechanism. So again, using the concept of normal distribution, because it is proved, it is understood that the mean of a large sample data is going to follow a kind of a normal distribution itself. Just to understand the world of normal distribution, when I try to plot the frequencies of the various observations, I try to see this is the shape that comes out for the typical frequency distribution. One, it is symmetrical, right, which means the values are equally distributed on both sides of the center. It is having a bell shape, as we are seeing in the picture. But typically these outcomes, they don't touch the x-axis, which means the value lies between minus infinite to plus infinite. Though as it moves farther and farther, the frequency is very much negligible. Frequency is negligible at the extremes, but it is not zero, remember, which means it will never touch the x-axis anywhere. It goes on and on up to minus infinite. So limitless extension towards the left as well as the right. And this graph is actually coming out, the equation that goes into this particular shape is defined by two parameters, the mu and the sigma squared, which mu is nothing but the mean and sigma squared is nothing but the variance. If I have these two things, the graph of this is very much generated, because the typical probability density function for this comes out as 1 by sigma root 2 pi e power minus half x minus mu by sigma square. from minus infinite to plus infinite, right? X is ranging from minus infinite to plus infinite. I'm going to get this kind of a function, which means the only parameters that it is using is sigma and mu, and that is what is generating this kind of a shape, right? So once I know the mean and the variance of a normal distribution, if at all probably I know that my particular data is normal, in general the returns are expected to follow a normal distribution. And once I know that it is a normal distribution, probably I can look at just computing the mean of it, computing the variance of it, and based on that I can find out the probability of anything, the probability that the return is less than minus 2%, probability that the return is greater than 5%. All these kind of probability related questions can quite comfortably be solved once I know the equation, or once I know the mean and variance of a normal distribution. That's one major aspect which forms a benefit for the normal distribution. And the other important thing is the skewness for a normal distribution is 0, which means the mean is equal to the median, which is equal to the mode for a normal distribution. And regarding kurtosis, it should be equal to 3, or the excess kurtosis should be equal to 0 for a normal distribution. So generally it's not a high peaked or low peaked kind of a distribution. So we are seeing the skewness should be 0, the kurtosis should be 3, or excess kurtosis should be equal to 0. And when I am looking at stock 1 returns following a normal distribution, stock 2 returns following another normal distribution, any linear combination of these two is also following a normal distribution. That's one more important result. Any linear combination of two or more normally distributed random variables also results in a normally distributed random variable only. Here a few things that we need to understand. If at all I am looking at only one variable, I call that normal distribution as a univariate normal distribution. But if I am considering two or more variables, I am looking at it as a multivariate normal distribution. I am looking at it as a multivariate normal distribution. So whenever I am getting into a multivariate normal distribution, I need to have the means of each of the distributions, each of the variables. I need to have the variance or the standard deviations of each of the variables, and along with that I need to have the correlation that are existing, correlations or covariances that are typically existing between each of the pairs of the normally distributed random variables. So if I am talking of n different assets, if I am looking at a multivariate normal distribution, I would be requiring n means, n variances, and probably NC2 correlations, because pairwise n into n minus 1 by 2 correlations is what typically I require. And the linear combination of two or more normally distributed variables is also a normally distributed variable. And any normal distribution which is having a mean of 0 and variance of 1, generally normal distribution is denoted by n of mu comma sigma squared. So any normal distribution with a mean 0 and variance of 1, I call it as a standard normal variable. Important thing in many calculation. Any variable, the reason why we need to understand this is any normal variable can be converted to a standard normal variable, right? So if the normal variable is denoted by n, which talks about having a mean mu and variance of sigma squared, the standard normal variable is denoted by z, having a mean 0 as well as variance of 1. So any normal variable value can be converted into a standard normal variable value by subtracting the mean from the observation and dividing it by the standard deviation of the observation. So the z comes from n by taking every value of n, subtract the mean from it, divided by the standard deviation. Right, so that is how I can convert any normal variable into a standard normal variable. So this this is a z distribution which is having a mean of 0 and a variance of 1, and the probability computation for the normal variable, if I want the probability that x is less than minus 2%, I can find out the equivalence of probability that z is less than, let's say, something else. Z is less than or equal to some p. So these two are more or less equal. Probably the better way I can put it is, if I am saying that x is following a normal distribution, let's say x is the heights of the people. I say the heights of the people follows a normal distribution with mean of 160 and the variance of 100. So I can write x is a normal distribution with a mean of 160 and a variance of 100. The same thing, probably I can convert the x into z. So if the question goes like, what is the probability that x takes a value greater than 180? Now this is same as answering this question is same as I convert this x in form of z, x minus mu by sigma greater than 180 minus mu 160 by sigma 10. So it is like, this is nothing but z greater than 2. What is the probability that z is greater than 2? Probability that x is greater than 180 is equivalent to probability of z is greater than 2. These two are one and the same. So even if I am able to compute this, and in general for the standard normal distribution, there are what are called as tables, standard normal distribution tables, which are given almost in every statistics textbook, or we can use the spreadsheet for it. So we can very well compute the probability that this is greater than this. So if I am able to compute the probability that this is greater than this, it's equivalent to computing the probability of x greater than 180. So that's the reason what we see, the standard normal distribution has lot more applications, because you can there is a tabular reference to it, and from where you could very well compute the probabilities of any kind of values, right? Now coming to the major application of normal distribution, we have been saying that the the returns, the asset returns typically follow a normal distribution. Though literally I have some kind of questions against it, but approximately yes, I can very well take that the returns typically follow a normal distribution, right? Because majority of the times we see that all the values, all the returns lie within plus or minus 3 standard deviations of the mean. And what is in reality what we see is, if I am seeing generally quarterly returns or annual returns kind of stuff, the behavior I see is they are more or less normally distributed. But when I am seeing them for a very short period, daily returns or weekly returns, probably there is a possibility of higher kurtosis in those kind of values, which means extreme values are probably the extreme values are much higher, fat tails are much higher with those kind of distribution. So there is a general possibility that the normal distribution is tending to underestimate the probability of the extreme returns. Underestimate the probability of extreme returns in general. So normal distribution, though in some cases is more and more applicable to measurement of the returns, but whenever we are talking about the returns of a portfolio containing some options kind where the asymmetric payoffs are going to come up, portfolios that contain asymmetric payoffs like options, probably the normal distribution is not a suitable tool. And normal distribution is not a suitable tool for modeling the prices. It's a decent tool for modeling the returns, but not for prices, because normal distribution actually doesn't have any boundaries. It can go from minus infinite to plus infinite, but the prices can go only from 0 to some infinite. They cannot have a negative value. So that's one of the prime reasons for modeling asset prices. I need that kind of a distribution which does not have any negative values, and that's where I refer to another distribution, which is the log normal distribution, which does not take any kind of negative value. So that's one thing that we would be looking at slightly later. So directly in this context, at least I can say that the normal distribution cannot have a negative value. And similarly, even from the returns perspective, what I could see is the worst case return is only 100%, whereas the normal distribution extends from minus infinite. So with a normal distribution, I cannot generate a value, or in reality the returns don't have a value below minus 100%, but the normal distribution can take a value below minus 100. So that's where, though in real world we keep using it, but if I have to talk about it in literary terms, it is not that possible to model the normal distribution, use a normal distribution for modeling the asset returns. And coming to few more important things relating to normal distribution, we see that approximately 50% of the observations lie between mean plus or minus 2/3 standard deviations. Similarly, 68% of the observations lie between mean plus or minus 1 standard deviation. 95% of the observations lie between mean plus or minus 1.96 standard deviations. 99% of the observations lie between mean plus or minus 2.58 standard deviations. So there is a lot of standardization that is associated with a normal distribution. Once I observe that my particular data follows a normal distribution, all these things are very comfortably accompanying the situation, right? So that's one more reason we can very well use normal distribution for a lot of purposes. Probably once I convert the normal distribution into a standard normal distribution, it becomes even more useful for it becomes even more advantageous to use it for large number of applications. So what we'll do is we'll try to look at one example of returns and see whether they are really following a normal distribution, and from that understanding of the normal distribution, let's try to find some of the probabilities associated with that. All right. Now suppose let me look at this data that we have used for statistical return. So I've taken right from January 1991 till October 2014 the Sensex values, and I've computed the monthly returns. Now I want to check whether these returns are normally distributed or not. So how do I check whether they are normally distributed or not? As we have just now understood that the skewness for a normally distributed random variable is almost close to 0. So I'll look out for the skewness. It is 0.54, slightly on the positive side. And what about the kurtosis? Kurtosis, if I'm looking at for the same for the same random variable, it is excess kurtosis is 2.49. So probably it is looking like there is some kind of extremities in it. So I am trying to identify a couple of extreme values that are there, right? As an analysis, I will try to find what are those extreme values that are there. So probably I am trying to see in this which is the largest value, right, so that I can remove it and see whether the values are coming more or less closer to normal. So almost 41.99% is the value which is the highest, so 42%. So probably I am finding the 42% here. So I would like to remove this one extreme value. Overall looking like the skewness is 22.22, which is very close to 0, and at the same time I am also seeing but the kurtosis still is lying at 1.23. So I would like to remove one more extreme value, 31.06, just to see. Yes, skewness has come closer to 0, kurtosis is still at 0.94. So just to create a possibility of normality, what I am trying to do is I am just trying to remove a few extreme values, because as we have discussed earlier, the major problem that we observe with the returns is the tails could be slightly fatter than the normal, and generally the normal distribution is underestimating the tails. That is that important thing which we have looked at even in our earlier discussion. So just to try to come in line with those things, what I am trying to do is I am trying to remove a few extreme, and if you see all these extremities, majority of them have occurred in somewhere in 1991, almost 20 years back data. But probably 28.26 is one more number which I want to look at. Right, probably that's the only observation which is slightly in the recent past, looks like. Yeah, here is where in 2009 May I am seeing a 28.26% increase in the value within just 1 month. But whatever it is, now if you see, as I am keeping to remove some of the values just with 4 or 5, though I had almost 280 odd observations, just by removing 3 or 4, I am seeing that the data is coming more or less closer to normal. Even if I remove this one more, yes, skewness is closer to 0, kurtosis is closer to 0. So probably I am seeing now some kind of normality associated with the data. Okay, fair enough. Now I am assuming, just for our understanding of the subject here, I am assuming that the data is following a normal distribution. So I will try to find out the mean of this normally distributed variable. So I'll take the average, I take the mean of this, it is coming to somewhere around 0.9%, right, 0.98%. I am taking the standard deviation of this normally distributed variable. So I am taking the standard deviation of this variable. I know that this is a normally distributed. Now, once I know that this is the mean, this is the standard deviation, what we are saying is, one, I want to find out what is the probability that x crosses 20%. With this kind of an intention, now I want to find out, now I know that the normally distributed random variable is just characterized by mean and standard deviation. Now based on that, I would like to compute the probabilities of almost anything. So here I want to calculate the probability that a monthly return is greater than 20%. What is the chance that the monthly return is greater than 20%? So that is something which I can convert first into a standard normal variable. So the z value, which is my standard normal variable, can come out as x, which is 20%, minus mu, which is 0.98%, divided by sigma. So z is 2.54. It's as good as now I saying what is the probability that z is greater than 2.5433. So both of them are one and the same. And probably if I look at here, there is something called norms dist, which gives me the value of the probability right from the extreme left. So here, just to showcase that this is my z, and I take it as a cumulative distribution function, this gives me that in the normal distribution, this gives me that if this is the normal distribution and if this is z equal to 0, which is the mean, this is 2.54. The area from here till this point is 99.45%. But all I want is z greater than 2.54, which means this part of the area, which comes out as 0.55%. So once I convert it into a standard normal variable, lots and lots of workout can be done on the top of that. I can find out the probability relating to anything just by looking at converting that regular random variable into a standard normal variable, and after that trying to map it with the tables, or probably in this case the formula, the norms dist, norm s dist. Norm is normal, s is standard. Standard normal distribution, I'm trying to find the value or the area which is corresponding to the probability associated with that standard normal distribution. So I can very well refer to the tables, and from those kind of tables I can very well compute the probabilities associated with almost any scenario. Right? Now, another application associated with the normal distribution, generally, as we have been talking till now, any investment, it is looked at from the perspective of returns as well as risk. So, assuming that the returns are following a normal distribution, I want to find out what is the probability that the return typically falls, let's say, below below 1%. I want to find out what is the probability that a monthly return falls below 1.5%. Right? I am having a target and I want to find out what is the chance that I'll fall below the target. Right? Even those kind of things can quite comfortably be understood once I know that the returns are normally distributed. And the major work of the portfolio framework, which is the mean variance portfolio analysis, that makes a very major assumption that the returns are normally distributed and the investors have a quadratic utility function. I'll talk about this investors having a quadratic utility function slightly later when I take up the economics part. But one major assumption is the returns are approximately normal. If not exactly, they are more or less approximately normal. And whenever I'm looking at a target, trying to find the probability that I go below the target, that is what I call as a safety first rule, or probably this kind of a concept otherwise called as a shortfall risk. So in this case, again going back to our example, if I want what is the probability that X falls less than or equal to 1.5%, I have a monthly target of 1.5%. So from there I'll compute my Z, which is 1.5% minus mu divided by standard deviation. So it's as good as saying probability of Z less than or equal to 0.0696, and I can take that into my norms dist kind of a table, wherein I am looking at this particular Z value, which tells me that it is 52.77%. There is a 52.77% chance that I will fall below the 1.5% target. Right? So this is the probability of my loss exceeding this 1.5, or probably my returns falling below a minimum acceptable limit. Right? So I have to choose that particular portfolio. If at all I am choosing any portfolio, I have to choose that particular portfolio whose probability of return is lesser than that target. I say this is my target. The portfolio's return, probability that the portfolio's return falls below the target is the minimum most possible. Right? I want to typically invest in that portfolio where the probability of the return falling below the target level is the minimum most possible. And for that I am always looking at in terms of the returns, targets and the standard deviation. So that is where an expression has come out which is called as Roy's safety first criteria. What this criteria is simply saying is, for every portfolio you try to compute the return of the portfolio, the expected return of the portfolio minus your targeted return, and you divide it by the standard deviation of the portfolio. And this is what we call as Roy's safety first criteria. And what is simply being said is, whatever the portfolio that maximizes this value, right, which again is using the same concept, the probability that the return on it is lesser than your targeted return should be the minimum most possible. The other way of putting the same is choose that portfolio which has the highest Roy's safety first criteria ratio. So whichever, probably now if I am saying that there is a portfolio which has given 10% return, and with a standard deviation of 8%, and there is a portfolio that has given 15% return with a standard deviation of 10%, and let's say my target return is 8%, then what is that I am seeing? I am trying to look at the Roy's safety first criteria for the first one. My portfolio return minus the target return divided by the standard deviation of the returns, so which is 0.25. And in the second case, portfolio return minus the target return divided by the standard deviation of the returns, which is 0.7. So probably I would be choosing the second one compared to the first one, going with the Roy's safety first criteria. And in this Roy's safety first criteria formula, instead of a target return, I use risk-free rate of return. This gets translated into a Sharpe ratio only. Instead of using the target return, I am using a risk-free rate of return. The safety first ratio gets translated into a Sharpe ratio, and even in case of Sharpe ratio also, the intention is choose that particular portfolio which maximizes the Sharpe ratio. So even the fundamentals remain the same, whether we are going for a Sharpe ratio or safety first criteria ratio. And another, as different kinds of applications, as we start understanding more and more of finance, we see that there are lot many applications of normal distribution that come into it. So a thorough understanding of the normal distribution, the various properties of the normal distribution, becomes more and more important if we have to strengthen our learning on the applications in finance, right? Then let's move on to one more distribution which has a lot of applications in the world of finance, which is the log normal distribution. Probably a better way to put it is, if the logarithm of the values, if the data does not follow a normal distribution, but the logarithm of the data follows normal, right? Data does not follow a normal, but the logarithm of the data follows normal. We say that the data follows log normal. So it's like, if x is a random variable, I see the logarithm of x is following a normal distribution with some mean mu, variance sigma square. Then I say x will follow a log normal distribution with mu and sigma square. That's the important relationship that exists between the normal and log normal, and that's one of the prime reasons log normal distribution is more comfortably used to model the asset prices, whereas the normal distribution is used to model asset returns, right? Prices are log normally distributed and the returns are normally distributed, and this again you find that this is a base for option pricing model, which is a Black-Scholes based option pricing model, which makes an assumption that the asset prices follow a log normal distribution. So the natural logarithm of those prices are going to follow a normal distribution. And why the log normal distribution is essential is it is bounded by 0. So it cannot take a negative value. Log normal distribution cannot take a negative value, and it is not a symmetric, but it is skewed to right kind of a distribution. The same logic happens with asset prices. On the lower side they are bounded by 0, but on the higher side they could take almost any kind of a value. So that's one of the prime reasons we see that the asset prices can quite comfortably be modeled using the log normal kind of a distribution. Now just to see here, these are the returns In some cases, what I can very well take is the log prices. Let's say if the prices are following a normal distribution, log normal distribution, I say log prices follow a normal distribution. So that's where I'm taking the logarithm of the prices. Or the other way which I can look at when I'm looking at the returns are following a normal distribution. So let's say if I'm looking at the logarithm of the prices follows a normal. So these are the logarithms. So I want to see whether the logarithm of these prices is following a normal distribution or not. So first let me try to find whether the data is following a normal distribution or not. Right? For Sensex, if I look at skewness, it's 0.82, and the kurtosis, if I look at for the prices, the kurtosis, if I look at it, is minus 0.78. But if I am looking at the logarithm, the skewness is close to 0.22 and kurtosis is close to, okay, kurtosis is much higher in this case, but in majority of the cases what we see is the prices will follow a normal distribution, but the prices will follow a log normal distribution, and the returns are more appropriately following a kind of a normal distribution. So in general what happens is, for the normal distribution, if mu and sigma squared are the mean and variance of it, even for the log normal distribution we define in the form of mu and sigma squared only, but this mu and sigma squared are the parameters of the underlying normal distribution, not for this log normal. So generally we have two sets of means and variances here. Generally we define in terms of the normal distribution only, but if I have to compute the mean of the log normal distribution, we say that the mean of that log normal distribution is e to the power of mu plus sigma squared by 2, and the variance of this log normal distribution is e to the power of 2 mu plus sigma squared multiplied by e to the power of sigma squared minus 1. So this actually comes out as the variance of the log normal distribution. This is the mean of the log normal distribution, but we define the parameters of the log normal distribution in terms of the mean and the variance of the underlying normal distribution, not the direct log normal distribution itself. So this is one more important point as far as the log normal distribution that we need to understand. And a few important relationships that I would like to discuss regarding the log normal distribution. Probably if I have to look at the relationship between the stock return, the stock returns and the stock price, what we simply say is stocks continuously compounded, the stocks continuously compounded returns. If they are normally distributed, so how do I find continuously compounded returns? I take the logarithm of S1 by S0. Instead of directly taking only the logarithm of prices, I take the logarithm or continuously compounded returns. If I say, it is nothing but I am doing the logarithm of S1 by S0. This is what we call as continuously compounded return, because B1 minus B0 by 0 B0 if I do, it's a discrete return. In this case, it's a monthly return. But for that same, if I take the logarithm of that 1 plus monthly return, that is what is nothing but a continuously compounded kind of a return. So that's where I am saying here, when I take the logarithm of this is a continuously compounded return. So in all these cases, if I find the continuously compounded return, I want to check out whether this continuously compounded return is following any kind of a normal distribution. So I could see the skewness of this continuously compounded distribution, which is giving me 0.07, but it could have a little bit of kurtosis, 1.66, but one or few extreme values I can look at and remove it. It becomes more or less perfectly normal. Okay, I mean, out of a data of 280 points, probably if I am just removing one or two, saying that they are extreme values and that too these values are very old, probably the normality is getting more and more better. Now, the point for me here is, if the stock's continuously compounded return is normally distributed, then I can say that the future stock price of this particular asset is going to be log normally distributed. So one important thing as a part of my modeling exercise, right? So stock prices follow a log normal distribution, and the continuously compounded returns of the same, they are following a kind of a normal distribution for us. And majority of the times, what we make as an assumption is the returns are independent and identically distributed kind of variables, IIDs. Independent and identically distributed. When I say independent, yes, tomorrow's price is nowhere dependent on the today's. Just by understanding the past prices, no one can typically make an assessment about the tomorrow's price or a future price. So that is the reason we call it as independent. And two, the identical distribution is more like probably the important characteristics like mean, the variance, they don't change over time. So they are more or less stationary kind of stuff. So that's one more important assumption that goes into lots and lots of the application building. So which means if the variance for one day, if the daily variance per one day is sigma squared, we say variance per 2 days will be 2 sigma squared. Variance per n days will be n sigma squared because of those relationships. So obviously the standard deviation for n days will become square root of n times sigma. Standard deviation per n times becomes square root of n times sigma because variance is directly getting added up. So the standard deviation is just becoming the square root of the variance. And so we can very well use the log normal distributions for the stock prices and the normal distributions for the stock returns. And we also have to understand that the log normal distribution is more skewed. It's not a symmetric kind of a distribution. So typically it fits much better for modeling of the stock prices. All right. Now, just that we have understood the different continuous distributions, we'll try to end this chapter with a small understanding of the concept of Monte Carlo simulation, which is very much essential for generating the data, provided we know that it follows a particular form of a distribution. All right. So whenever we talk about Monte Carlo simulation, It's basically a computer-based technique for generating data on a random using random numbers. I generate large volume of data and based on a specified probability distribution. So I can generate probably thousands of numbers which follow a normal distribution, or probably I can generate thousands of 10,000s of values which can generate a log normal distribution. So Monte Carlo simulation is more or less trying to address that. So which means from a benefit perspective, if I look at for the Monte Carlo simulation, I can try to probably test my model before implementing it, because it's simulating the real world scenario. So probably helping very heavily in testing the model before implementing it, right? Which means it helps a lot in the planning process. So the way we can generate, just giving you a simplified scenario, in a spreadsheet, I can use a simple formula called RAND. This RAND as a formula actually generates random numbers at randomly between 0 and 1. So let's say here I will generate some around 5000 random numbers. So it is generating the random numbers. All these numbers follow a uniform, continuous uniform distribution. Based on that continuous uniform distribution, random numbers are generated between 0 and 1. Now what I can do is I can convert them into a standard normal variable. Standard normal generated random observations by using the inverse of the normal function. So what I can simply say is I'll use a norms inverse as a function and I map it to this particular probability. So what happens, whatever the numbers that I am getting here, they follow a standard normal distribution. So just to understand, see whether they are following a standard normal distribution or not, I can look at finding out their skewness. I'll try to find out the skewness of the values very much closer to 0, and I'll try out finding out their kurtosis. Even the kurtosis, the excess kurtosis is again very much closer to 0, which means these observations that are generated for me are standard normal observations. Similarly, once I am able to generate a standard normal, I can always associate a mean and a variance, and I can generate a normal observation as well. So the different possibilities, different scenarios for different variables based on the underlying probability distribution, I can simulate multiple possibilities, and based on that try assessing my computation. So whichever is a very complex to operate kind of a scenario, I can very well generate the observations using the Monte Carlo simulation. So that's where probably if there are some kind of a complex securities whose valuation models are more or less difficult to implement, probably different kinds of exotic options where direct formulas for finding out the premiums are not there, no analytical pricing formulas or no analytical solutions are there for some kind of securities, or probably when we are talking about some complex securities like mortgage backed securities, or whenever I am looking at securities where there are embedded option like features like convertible bonds, etc. All these kinds of securities doing a valuation a physical way, it's almost close to difficult. So that's where probably Monte Carlo simulation is really helping us out. But of course, the simulation is as good as the underlying assumptions that we use to generate it, the underlying probability distribution. So it's the job of the analyst to specify what is the distribution that what is the probability distribution he would like to associate for that particular variable. So based on that only the values can be quite comfortably generated. So even as a part of sensitivity analysis, change the variable a little bit and see what is the kind of impact. So all these things are quite comfortably be addressed using the Monte Carlo simulation itself. But to get a betterment using the Monte Carlo simulation, what is the number of trials or number of experiments that I have to go with? Now that is what is being said. The larger the number, thousands, tens of thousands, so larger the number, the better is the accuracy. And today generating 10,000s of observations is nowhere a difficulty, given the systems are very much effective in terms of their computing power. So always we can start with a random number generator, which actually as I said is a rand function in a tool like Excel, which will generate some random value based on a uniform distribution of 0 between 0 and 1. Then I can use what is called as inverse transform method and use that method to typically transform the uniformly distributed random variable to an equivalent random observation matching some other distribution. So which means almost any distribution can be simulated using the concept of random numbers and a Monte Carlo simulation mechanism. Once the values are simulated, we can do any kind of calculations and we can do the pricings, values, finding out the probabilities of something lesser than something, greater than something. All these kind of things come in more handy. So just as a summarization of the Monte Carlo simulation, a few things that are essential is the probability distribution of the underlying variable needs to be understood to the fullest. Whereas on the other side, people even talk about historical simulation, wherein I am not trying to find any kind of probability distribution, but just taking the past values of that underlying variable and I am trying to randomly select a few of them. A random selection of few of them and try to make the necessary computations. But here, okay, on the positive side, probably they are a most direct evidence of the existence of the data, but at the same time, whichever the values have not occurred in the regular scenario, they will not occur even in our simulated scenario as well. But in case of Monte Carlo, even if some extreme value did not come in our regular scenario, it can very well come in the simulated kind of scenario. So that's where Monte Carlo simulation has much more advantage compared to the historical simulation approach. And what we typically say as a final note is, it is not a replacement to analytical methods. If I have a good formula, probably the analytical method is much better. But what we are saying is it should be more of a complement to the analytical method. So wherever I am not able to get a good analytical method, good formula, or the formula relationship becoming more and more complex, it is in those kind of situations I should look out towards this Monte Carlo simulation as a solution. Alright. So that's what I wanted to look at as a part of this common probability distributions, starting with the discrete probability distribution, slowly understanding the continuous probability, and one of the major applications of this distributions, which is the Monte Carlo simulation, how we can generate the observations based on the distribution of the underlying variable. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.